I'm good. I'm good. I ate so much as a kid. I just learned to eat. I can taste it.
Michael, you cannot taste it.
Taste the science, mister.
Alrighty, so we're back to it for another week. I just got one more quiz to grade for you guys, and then I'll get all that stuff back to you on Wednesday there. But other than that, we were making our way through chapter 5, and the theme of chapter 5 is just where the energy goes, right? Whether it goes into or out of, from the hot to the cold, from the high to the low, whatever you want to say with that. I think, as I've mentioned a couple of times at this point, the tricky part of chapter 5 is just figuring out what the world of questions are asking you to do. Kind of reading and interpreting the data and putting it together to something coherent. And then once you can actually read it, then it just comes down to the Q equals MC delta T is the really the only equation that we will use. Although we'll talk a little bit about enthalpy, but we'll come back to that a little bit later. And enthalpy is just basically a modification of the formula for Q, but we'll talk about that in just a minute. But anyway, before we get started, let's just open in prayer, and then we'll continue on. But Lord, we just thank you. We just thank you yet again, Lord, for another day and another opportunity. And Lord, we just thank you for the world around us that you've created, Lord, and just help open our eyes to the beauty that you've seen, that you've made here, Lord. Just help us to see it with your eyes. And Lord, just help us to be good stewards of the things that you have given us. Not just the physical possessions, Lord, but also be good stewards of our spiritual possession and of our time also. Lord, just help our time to be productive and fruitful, and just help it to be something that builds your kingdom here, Lord. Just show us where it is that you would have us work, Lord, and just open our eyes to see these things. And we ask this in your name. Amen. All right. So, do hope you guys had a good weekend. I actually took a little bit of time off, so that's also why I didn't finish grading things. So I'm ready to wear myself out again with entropy and enthalpy and calculations of Q and all this tedious stuff that we have to do in chapter 5. But we'll make our way through it. Where we had ended up on Friday was with this question here. One of these standard questions, right? These thermal equilibrium questions. You put something hot in with something cold, and they ask you to usually find the final temperature, or they might ask you to find the specific heat of something, or whatever it might be, okay? All it comes down to is kind of remembering that thing at the top there where we talked about, what is lost has to be gained, and whether Q is positive or Q is negative, and recognizing to make sure that you put the negative sign, otherwise your math at the end won't quite work out the proper way there, okay? But other than that, it's just an application of the Q equals MC delta T. All right. So from there, we just kind of have one more equation which we've talked about a bit, but just to kind of put a fine point on it. When we're talking about the change in energy, that's just Q plus W, right? Q is what we've been calculating, so we could kind of build upon that a little bit there, right? And we talked about the terms of endothermic and exothermic, and I believe the last thing we kind of introduced was the concept of phase changes, and that there's energy involved with phase changes of materials from solids to liquids, or liquids to gases, and then in the reverse also. One of the concepts that we'll come back to, hang on just a second. One of the concepts that we'll come back to probably today, I'm pretty sure we'll get to there today, is Hess's law, and Hess's law is going to play off of this idea here, right? If we go forward in a reaction and it releases energy, if we go backwards in that reaction, then it's going to be the opposite, then it's going to absorb energy, is what it is, okay? So I'm going to come back and play off of that idea there in just a little bit. Right? You have a question?
Yeah. Change in energy is Q plus W, W is work, and Q is
heat, energy, entropy. Yep. Not entropy, excuse me. All right. So just two quick questions just to kind of knock the rust off here. cools, transfers as much energy to the surroundings, no work is done. That is delta E. Again, the tricky part is just figuring out what in the world the question's asking. What is and isn't important. Probably don't even need your calculator for this one. What in the world is going on in this problem here? So we've got a liquid and it cools, okay, fair enough. It tells us that it transfers 911 joules to the surroundings. So what does that bit of information tell you? The liquid loses energy, right? Now, why is it important to recognize that, or to call that out, or to make a note of it, or whatever you want to say? What does that tell you? Yeah. Whether it's gaining or losing energy, which tells us about the magnitude of Q, right? Is it positive or is it negative, right? Because if I lose energy, what's Q? Negative, right? If I gain energy, it's going to be positive. You guys with me on that one, right? Because I just tell you that it transferred energy. Doesn't necessarily tell me whether I gained or I lost it, although that's why I give you guys the temperatures there, right? Because what does the temperature tell you? Well, it went from hot to cold. So what happened? Q has to be negative. And I say that no work is done by the system, so that's easy enough, right? Where did my... there it is, right? So work, oops, that didn't quite do anything, right? So work is equal to nothing, okay? Q is equal to negative 911 joules, and it asks us what delta E is, right? Well, delta E, just from the previous slide, is equal to Q plus W. Okay, so delta E is equal to negative 911, right? Not too bad, right? Yeah, what's up?
So we can't say that Q is equal to negative 15 degrees Celsius because Q is in joules, joules is energy. Is that correct?
Well, Q is not equal to just temperature, right? If we wanted to calculate Q, then we need the mass and the specific heat and that kind of information with it, right? We give you the temperature just to tell you, hey, look, we're losing energy, right? We're going from hot to cold. Just to kind of put a fine point on the whether Q is going to be plus or minus. Okay? Not too bad, right? All right. Let's continue on with this thought here then. Let's see what happens here. Yeah. Sure. Okay.
I'm just like I know you have all the information, I was just
Yep.
trying to say, so why is it negative?
Because it's losing energy, right? The change in energy is going to be negative, right?
So it's
Because we're going from hotter temperature to colder temperature, right? 45 to 30.
so is the change in E just negative?
Mm-hmm. That's it, yeah.
Okay.
Work is equal to 0 and Q is equal to negative 911, right? So we just plug Q and W into the equation. Right? All right. About the same idea here. close attention to the wording and what it tells you about the magnitude of these values. What's that? Yeah, 50 is what? Okay. Alright, so again, let's take a minute to kind of just, break apart what in the world this question is asking. So we have a thing, our system, that does work on its surroundings. Alright? It does work on its surroundings. So what does that tell you about the magnitude of W for the system? If it does work, right, it's basically using energy to do that work, right? It's like if I ask you guys to go do some push-ups, right? It'll take energy for you guys to do that work. So what does that tell you about the magnitude of work in this case? It's going to be negative, right? It takes energy out of you, right? It takes energy to do the push-ups. So for the system, work is going to be negative, right? 50.2. But then it says the surroundings add energy into the system. So what does that tell you about the Q value there, the heat? That's going to be positive. You guys with me on this one? There we go. We put these two together. Delta E, Q plus W, right? Q is equal to plus 90.1 joules. Work is equal to negative 50.2 joules. Oh, okay. Right, and then we just put these two together, right? Delta E then is equal to, I got plus 39.9, right? Cool. So if they give you some information about work, you might have to calculate Q, right? But Q is equal to MC delta T, right? So that's not going to be any different. So once we figure out Q, then we can start to figure out changes in energy and these kind of things. That's all we're getting at here. Paying attention to exothermic, endothermic, work going in, work going out, that kind of thing. Yeah?
Wait, why is the 50.2 negative?
Because it says work is done on the surroundings.
Oh, okay.
So the system is doing something to the surroundings, is what it is.
Okay.
Mhm. Good? Yeah, what's up?
Are we gonna see examples of like what the words say that it's not, that it doesn't do work, that it's not?
If it doesn't do work, the last one did that, right?
That was it?
Mm-hmm. If I remember correctly, right? Wasn't the last one work equal to 0?
Oh, yeah.
Yep. Cool, alright. So now I'm gonna introduce a scary word that you guys aren't gonna like. Okay? I know. Right? One of many. But don't worry, it's not the M word, right? But it involves math. So we still have to be kind of scared of it. So we talk about enthalpy. Now enthalpy sounds fancy, but all we're going to be measuring, like it says there at the top, is the heat transfer at a constant pressure. Okay, so what in the world does that mean? Well, how do we measure heat going into, or excuse me, how can we calculate heat going into or out of a system? What formula could we possibly use for that? What formula measures Q, or what's Q a formula? What is it? Well, it's an unknown, I guess, right? I guess we'll just have to figure it out, right? You guys get the point I'm making? If we're gonna look at heat transfer or energy going into or out of the system, it's just Q. The conditions are that we're at constant pressure, right? That's gonna simplify some of the math for us. So what does it mean to be constant pressure? Are you guys at a constant pressure right now? Physically, maybe not emotionally, right? Okay. I don't know, Dr. H. It's starting to get kind of difficult. So if you guys did a reaction on the bench top in front of you, Would that be at a constant pressure? Well, sure, right? You guys have a beaker, you pour stuff into it, you stir it around. Does the pressure change? No, we're still at essentially 1 atmosphere, right? When would the pressure change? Well, if you have a sealed system, right? So all we're saying is that we're just calculate Q at a constant pressure. That's all it really comes down to. And then it kind of explains a little bit of what we're talking about there. Right, at a constant volume, right? V fixed volume, there's no motion, so work is 0, blah, 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 yada, 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 this kind of stuff that you guys can look up, right? And this is what we need to think about down here, right? The enthalpy is equal to Q at a constant pressure, right? That's what that Q sub P stands for there, okay? Now we're going to expand on this a little bit here, but I just wanted to define the idea there at constant pressure, right? So when it talks about enthalpy, it's going to have to say something about the pressure, or we can just say, or we can just assume that it is at constant pressure, okay? As soon as I say it changes pressure, then we have to worry about other things. We have to take care of work, and then it becomes too much like physics, and I don't like it, okay? So, all right. Some of you guys copying things down. All right. So let's think about this for just a second, or let's take a look at an application of this. Well, let me scroll down for just a second. Is this what I want? Yep. Sorry. So we'll come back to that other slide in just a second here. But when we're talking about enthalpy, right? What we're typically going to see it used for is the question there that's on the previous slide. We're going to heat things up, or we're going to look at transition between phases. Right? We're going to look at dissolving things maybe, we're going to look at reacting things a little bit later on, right? But we're just measuring the heat going into or out of the system is what it comes down to, all right? There's going to be some information that we need for this. We're going to need the values for the enthalpies of fusion, or the enthalpies of crystallization, or the enthalpies of condensation or vaporization. Right? These are these massive tables that you guys see, I believe, in the back of the book. I don't know if I flip through here for just a second. I think it's like Appendix G or something like that that has all this stuff in there. Yeah, it looks like stuff in Appendix D and C, right? So all this stuff that's in the back of the book, right? If you guys ever look through and you see this massive text dump that's at the back there, right? You guys might need those when you're working some of the problems in there. So Appendix C is what it is. Okay, so these are not values that I expect you guys to memorize. I'll either have to give you information about them directly, or I'll have to ask you guys to calculate them based off of some values that I give you. Okay, so it's not like I expect you guys to know the enthalpy of fusion for water, right? Now, what do we notice about this though? So we're saying with respect to water, when we go from a solid to a liquid, right? So solid to a liquid. So we're going from the solid state to the liquid state. So that's going to be an endothermic process, okay? We have to add energy into something to melt it. Well, I think you guys already knew that though, right? So it's, if you hold a snowball in your hand, right? Your hand gets cold, but the snowball warms up and it starts to melt, right? So you transfer energy into the snowball is what it is. And you'll notice that it takes 333 joules per gram of water. Pay attention to the units with this, okay? It's joules per gram, not joules per mole or anything like that, okay? If we go from a liquid to a gas, that's the enthalpy of vaporization, 2,260 in this case. Okay. And then the last two, you got a question?
So what you're saying is this is basically the mathematics and science behind melting frosty?
I mean, if we wanted to calculate how much energy it takes to melt frosty, yeah, right? We have to weigh it, and then we could figure out how much energy it takes to do that, is what it is. Okay. Now, what do we notice about the enthalpy of freezing and the enthalpy of condensation? Well, they're just the negative values of the fusion and the vaporization directly, right? Now, this is what we started out the day with. I said if you go one way with a reaction, right, if you go the reverse, we got to change the energy, right? If we release energy going one way, we absorb going the other. And that's all we're talking about here, right? It takes energy to melt something. It releases that same amount of energy as you freeze it or condense it back, okay? And that's what we're just talking about here, right? So remember delta H, right? And for us, delta H is just equal to Q is what it is, okay? But here's something important to think about. It's going to change our math a little bit. Now, what are the units on these energy values here? They are joules per what? Gram. Now, what are the units on specific heat, usually? Joules per gram what? Degrees Celsius, right? So we're missing a measure of temperature here. So you guys see what I mean with this?
It's regardless of temperature?
Sort of. What temperature does water melt at? 0 degrees. What is the range of temperature that water melts at? Well, it starts at 0 and it ends at 0. Right? So what's the change in temperature for melting? There is no change. You guys get what I mean with this? The point I'm making is that when you melt or when you boil something or when you freeze it or when you condense, whatever, those are at constant temperature. So what does that mean to our formula for Q? Normally Q is what? MC delta T, right? Well, what's the delta T if we're at constant temperature? Well, there isn't one, right? We just have to leave that out. So all that we care about here is the mass. Because you'll notice the units are what? Joules per gram. So let's say that I had 10 grams of water as a solid. How much energy would it take to melt that? So I have 10 grams of water as a solid. How much energy would it take to turn that into a liquid? Well, 10 times 333, that's it. You guys with me on this one? So when you're doing your phase transitions, we don't care about the temperature because the temperature stays the same. Got it?
Yeah,
Sure. Temperature change, right? The temperature stays the same at the phase transitions to calculate for our calculations.
So,
So no matter, like what if, never mind, I'll find out for the next question.
Okay. What's up?
so I guess as you're melting ice water, it's the same temperature until
Right.
So how does the
Well, be careful, right? Because now we're trying to get into what happens in the real world versus the mathematical world, right? The modeling world. Whenever water hits 0 degrees Celsius, it's going to start to melt, is what it is. Or freeze if we're going the other direction, right?
But it's just like those that water at that time, it's frozen until.
Right, because we're talking about how much energy do we have to give it to melt, right? So we're just transferring energy. It doesn't necessarily mean that we're heating it up continuously, right? Yeah.
So if we got, like, in this hypothetical situation, water is perfect water and exactly 0 degrees, it's
Yep.
gonna be both.
Yeah, so we'll get into that idea a little bit later when we get into phase diagrams, right? So that's a good point, right? If it's just water at 0, how do we know whether it's melting or heating up? The answer is we have to give you information about which way we're going, right? But it exists in both, right? It exists at an equilibrium. Some of it's melting, some of it's refreezing, right? So we just have to push it in one direction or the other, okay? All right. So all that being said, right? All that being said, how much energy does it take, or how much energy is transferred if 7.5 grams of ice at negative 10 degrees Celsius is taken to 120 degrees, okay? All right. So, how do we tackle a problem like this? Okay. Give you guys a second to copy it down, and then I'll scroll back up here. So the way we're going to tackle this problem is by thinking of it, ignore this for just a second. Right? The way we're going to tackle this is by thinking about each part of that energy transfer as a separate step. Okay, the question is saying we start at what, negative 10, right? And we go up to 120. So what happens first? We have ice right? That's at some low temperature. We add energy until it hits 0 degrees Celsius. And we can calculate that using Q, because Q is equal to M, C, and delta T, okay? So once we take our little ice cube and it hits 0, then we have to melt it. And that's gonna take a certain amount of energy. Once it's all melted, then we start to heat up the liquid water. Okay, once we get the liquid water to 100 degrees Celsius, we have to boil it. And once we boil it, we heat up the steam to 120 degrees Celsius. Right? So we're heating ice, step 1. We're melting ice, step 2. We're heating water, liquid water, step 3. We're boiling water, step 4. And step 5 is we're heating up steam. You guys catch this? Step 1, heat up the ice. Step 2, melt the ice. Step 3, heat the water. Step 4, boil the water. And step 5, heat the steam. Okay? So now we need a little bit of information. So let's start with step 1, right? Step 1 is heat the ice. So if I want to measure energy transferred into the ice, what magic formula are we going to use for this? Well, we got to calculate Q, and Q is equal to what? MC delta T. Do we know how much ice we have? Are we given a mass? Yes. Are we given a change in temperature? Yes, right? Because what's our change in temperature going to be? It starts at -10, and we heat it up to what? 0. You guys with me on this? Alright? What's the thing we're missing though? So we're given mass, like mass equals 7.5. Our change in temperature is T final minus T initial, okay? Which is equal to 0 minus a -10, right? And C of ice, it's previously in your notes, but if we look in the back table there, we can pull that value out, 2.05 joules per gram degree Celsius. Yeah?
A solid liquid.
We haven't done that yet. We haven't done that yet. All we're doing is taking ice at -10, where it's still solid,
Yeah.
all the way to 0. Once we hit 0, then we gotta turn it into a liquid.
Okay.
That's step 2.
RC, we should choose the one.
That's the phase it's currently in,
Okay.
right? Ice remains in solid until we melt it at 0, right? Of course, you see there's a couple of assumptions in there, right? We have the perfect ice cube that melts uniformly, right? Right, there are a couple of, yeah,
So what is C again?
C is a specific heat, right?
Of ice?
Of ice. Yep, yep. So can you guys plug that together and get a value? Q equals MC delta T, right? Q is equal to 7.5 grams. Specific heat, 2.05 joules per gram degree Celsius. And we'll put plus 10 here, right? So 0 minus a -10. If I put that all together, I got a value of 153 joules. Good? Is there anything different that we haven't seen so far? Well, it sounds more confusing, right? But is the math the same? Sure, right? Yeah, what's up?
How come with the energy change you don't consider the one
We're doing this step by step. Remember I gave you guys 5 steps we have to do, right? Step 1 is heat the ice. All right, so now our imaginary ice block is at 0 degrees Celsius. What happens to ice at 0 degrees Celsius? It'll melt, right? But it'll remain at 0 degrees Celsius. Okay? So step 2 is melt the ice. Which means ice to liquid water, right? So what we'll need for this is that information here, right? When we go from a solid to liquid, we'll need our value there for that enthalpy of fusion, okay? Remember, we don't have a value of temperature associated with this, right? All we have is joules per gram. So what do we have? Well, what's our mass equal to now? Well, we start out with 7.5 grams, but we heated it up, so what's our mass?
7.5.
It's still 7.5, right? Because what do we know? Matter can neither be created nor destroyed, right? So mass is still equal to 7.5. In fact, what will mass be for everything in this problem?
7.5.
You guys got it. All right. So delta H, right, is equal to 7.5 grams times 333 joules per gram.
And delta H is, where did you get that equation from?
The what?
Delta H equation, is that just?
That's the heat transfer at constant pressure, right? The enthalpy of fusion. You can just think of it as Q, right? Because if you go back in the notes, as you said, enthalpy is equal to Q at constant pressure, right?
Yes.
I'm just trying to scare you guys with a new value. Is it working? The stunned silence. It's okay, right? Okay, so all we gotta do is 7.5 times 333. Like 2505 is what I got? I like my answer better. unless I goofed on something. Yeah.
Help me to understand.
Yep.
When you put energy into the system.
Yep.
And specifically on like number 2, where it doesn't necessarily change in temperature.
Yeah.
Where does it go? Where?
It goes, yeah, oh, great question. So hang on to that thought for about a chapter and a half. It's gotta go somewhere, right? So, but the question, your question then becomes, how does something melt? Why does something melt? Right, that energy goes into breaking the bonds in between the individual water molecules.
I thought that released energy, or released heat.
No, it takes energy to break bonds. When you make new bonds, it releases. That's why when you go in reverse, right, you get energy back, right? Yeah.
Oh, you have to remember, like for water in this case, are we gonna have to remember the 0, at 0,
No.
it melts.
Or what do you think?
So, you're saying at 0, it either melts or freezes?
Yeah.
So, we have to remember, like, specific temperatures for other,
No. I expect you guys to know it from water because,
Okay.
well, I think that's just kind of knowledge everyone should know. Yeah, but I'd have to give you information about something else. I think, in fact, if I remember correctly, I was looking in the book and I had like this exact question, but they used something called benzene, right? And they told you where it melted at,
okay.
right? But how would that change anything? The answer is it really doesn't. All that it changes is your initials and your finals, right? Okay? All right. So what do we have now? So now we've melted our ice. So we have liquid water. What's step 3? Now we have liquid water at 0 degrees Celsius, and what do we do with it? Heat it all the way to what? 100, right? Because what happens to water at 100 degrees? It'll get converted into steam, right? So heat liquid water. Okay? Do we have a change in temperature associated with this? Yes. Do we have a mass still? Yeah, so we've got M, we can calculate delta T, and we can look up C, right? So mass still equal to 7.5 grams. C of liquid water, 4.184, right? Joules per gram. And delta T, T final is 100, T initial is 0, right? I know I'm giving you guys an eye exam there in the back, I'm sorry. I should have given you guys more room to write this. You guys with me on this one? Our mass is the same. We look up our specific heat capacity there, right? We have delta T. So we're making spaghetti is what it is, right? We got to boil the water. Yep.
Wait, how come we're doing MC like delta T for the third step, but for the second step we have to do change in the heat? I just don't know why we're doing that.
What temperature is this done at? It's at a constant temperature. There is no change in temperature. So all we care about is the mass and the heat that's involved with it. Make sense? Let's see, where's my math on this one? There it is. I got 3138 joules. Okay. So now we've got liquid water at 100 degrees Celsius. What happens to liquid water at 100 degrees Celsius? It's going to boil, right? So now we've got to boil water. I gotta be careful, right? What I mean with this is we gotta convert it from liquid to gas, right? What temperature does this happen at? 100, and that's at a constant temperature, right? So what do we need here? We need our mass, still equal to 7.5, and we need our enthalpy of vaporization, right? And that is equal to 2260 joules per gram, right? So delta H here, 7.5 times 2260 joules per gram. And there it is, 16950 joules. All right, one last step. Now we've got steam at 100 degrees Celsius. Where do we got to get it to? Steam at 120 degrees Celsius. So 5, heat the steam. I hear you. Okay, our mass is the same. We need the specific heat of steam. C of steam is equal to 1.99 joules per gram degrees Celsius. And our change in temperature, T final, 120, minus T initial, 100. Yep.
How come it takes less and less amount of energy to heat up the
Good question.
thing?
Good question, right? Good observation. I'll answer that for you again in about a chapter and a half. But that's an interesting observation, right? Now I'll get back to that in just a second. So hang on to that thought. Okay? And if I did my math, 298.5, right? Joules.
So we just alternate back and forth.
Yep. That's not too bad, right? What's the tricky part about this? Two things that I think of at least. One, understanding what happens when you melt or you freeze something. Those are at constant temperature, okay? And two is just conceptualizing and breaking everything down into individual parts, okay?
So don't we have to add us all the way?
And so that's the question. Which one of these 5 steps is our answer then? Well, what did the question ask? How much energy is transferred, right? How much energy is transferred when you do all 5 of these steps? So our final answer for this would be what? 153 plus 2505 plus 3138 plus 16950 plus 298, right? So you have to add all that stuff up. And for some reason oh yeah, what's up?
So for each kind of temperature of like, keep the ice, wood, and all that stuff.
Yep.
I just have to know the temperature of each thing, like already.
Where the phase changes happen?
Yeah.
Yes, yeah. Now, if it's something you guys aren't familiar with, then I'll have to give you that information. Right, I could give you, ethanol boils at 78 Celsius. And then you could go through the same rigmarole with that. Except once you hit 78, then you have to do the phase transition.
Okay, and so how much degrees is that?
Yeah, so that's where we ended up, right? It's taken to 120 degrees Celsius, right? Yeah. We could have said whatever number there, but that's it. Good? What's the final tally on everything here? What is it, 891.5 joules? Cool. All right. Very nice. Now knowing this, right? Now doing the trickier problem here. Now we can go back and take a look at this one here, right? So let's call this pseudo homework for you guys. See if you guys can do this one on your own, right? Remember, here's the visualization for this. How many steps is this gonna take? Well, we start at -50. We gotta heat it up to 0. At 0, we melt it, and then we take it up to +50, right? So how many steps are there? Just 3. Got it? So only 60% of the work from what you guys just had to do. Easy. Oh, I did have more space. I just crammed it together. All right. Well, lesson learned. All right. So just real quick as a definition, and this is going to help us with our math in just a minute. Well, maybe not a definition, just an idea or a concept to point out. Enthalpy is a state function, right? So what that kind of means is it doesn't matter how we get to where we end up, right? So it'd be like, okay, I want you guys to go to the Walmart that's in town, right? There's a couple different routes you guys could get there, but at the end of the day, you guys all end up at the Walmart is what it is. Okay, that's kind of what a state function is telling you. Right, and this is just a mathematical way of expressing this, right? If you have if you have 2 independent samples of water, heating one from 20 to 50 and cooling the other one from 100 to 50, at that final, right, at the end, right, your H and your volume and your pressure and your enthalpy, all that stuff's going to be the same. That's all it's talking about there, okay? And we already knew that because temperature is a state function. If I ask you to heat something up to 50 or cool something down to 50, where do you end up? At 50, okay? So the same idea is at play here, right? All we're talking about is that it's path independent there, right? Okay. All right, so now we introduce the next idea here. And this idea is that if I burn something, it releases energy, okay? It's a complex idea that fire hot, all right? You guys already knew this, right? You guys already know that fire hot because if you were like me as a kid, we played, touch the stove and I'm a dum-dum, right? So you guys all learned this at some point in your life too, right? But now what we can do is take this idea of enthalpy and actually calculate how hot that fire is. Or we can measure the energy released by the combustion, in this case of methane, okay? And so if we take a look over here on the right-hand side, we have values of delta H, the little knot symbol up there, the little degree symbol is just saying at standard value, which is 1 bar, okay? Don't worry too much about that, it's just the standard enthalpy for that reaction is what it is, okay? But take a look at this. So at the top reaction, we have methane, the CH4 plus oxygen goes to CO2 gas plus water as a gas. And that has an enthalpy value associated with it, okay? Right below that, we have almost an identical equation except for we make water as a liquid. And we note that there is a change in the enthalpy of that reaction, right? Water as a liquid releases significantly more energy than water as a gas does in this reaction. You guys see that? Right? Negative 803 versus negative 890. So what does this tell you? It tells you a couple things. First of all, you gotta pay attention, right? You gotta pay attention to the physical states of everything. Because again, if you go to that appendix C that's in your book there, be careful when you look up delta H of water as a liquid, as a gas, as a solid, whatever it might be, okay? So you gotta make sure you're writing your proper equations with this, whether it's a solid, liquid, or gas, okay? Delta H is also a per molar value. All right, so what does this mean for us? Well, really what I think about, or the idea that I keep in mind, is that this is now a product of my reaction, okay? This is now a product of my reaction. What I mean is, for every 1 mole of these and 2 moles of that, when they are combusted, I release 890 degrees of energy. So per mole of methane, I release 890, okay? So it's part of my balanced equation if you just want to think about it in that way. Good. All right, let's see if we can take this from abstract idea to practical problem then. Maybe kind of put a fine point on this. So there's a...
Is this the full plan right?
Yep, that's all I have. It's pretty simple looking at the end of the day, right? We have a reaction. We say how much heat is released from 10 grams of aluminum. Reacts with excess, yada, yada, yada. Iron dioxide, right? Okay. So what nice keyword do you guys see in there?
Tremendous.
Tremendous. Yeah. Thank you. That's what I was looking for.
Released.
That's something that's important. Hang on to that thought, right? So released tells us something, right? It tells us what? That energy is given off by this reaction. So what should the energy of the system be? That energy of the system should be negative, right? Very important. Okay. What other keywords do we see? Excess. What does excess tell us? Enough of what? Of what?
Rust.
Iron 3 oxide, right? Iron 3 oxide. So what? It tells us that we have the excess. What else does that tell us?
We're all tired.
What else does it tell us?
Limiting the lunar weight.
The limiting reactant, right? You guys with me on this one? Don't forget, right? We should always pay attention to the limiting and the excess reactants, right? So now that we know what the limiting reactant is, now we can go through and do our calculation. Alright? So what do we need to do here, right? What do we need to do? So we need to get, let's see, grams, right? We need to get grams into units of heat. Grams into joules is what we need to do. You guys see what I'm saying here? Right? The question's saying how much heat is released. We're given information in grams, so we have to convert grams into joules. Or kilojoules, or whatever it might be, some measure of energy. Got it? Well, do we have a direct conversion from grams into joules? No. Right? As a big shocker, what do you think the first step we have to do is? Grams into moles, okay? So let's do that. So convert grams of aluminum into moles. And 706, whoops, 3706. Alright. Okay, so now for the last step, we go back to what I was telling you guys there earlier. Now the heat becomes part of our reaction, right? The heat becomes part of our reaction. So we can use this in a stoichiometric way. Here's what I mean. So we are in values of moles of aluminum. So work through a mental exercise with me here for just a second. Let's say I need to convert moles of aluminum into moles of iron. Right? How would I convert moles of aluminum to moles of iron? What would I have to fill in here? What values would I need to convert moles into moles? Begins with an S.
Stoichiometry.
Our stoichiometry, right? Our balanced chemical equation, right? So we need to say, okay, for every 2 moles of aluminum, we have 2 moles of iron. And we can convert moles into moles. You guys with me on this one?
Yes.
Okay. So now our delta H is part of our balanced equation. So what does this tell us? Well, it tells us that for every 2 moles of iron, 2 moles of aluminum, I make what? Negative 851.5 kilojoules of energy. Okay? You guys with me?
No.
This is part of our equation. It says when I react 2 moles of aluminum plus 1 mole of iron-3 oxide, I release that much energy. Okay? For every 2 moles of aluminum, I release negative 851. It's just like a product, right? Our heat is a product of this reaction. It's stoichiometrically related to everything that's in there. Got it? So once we have a balanced equation, we can do this conversion. And I got negative 158 is what it is. Kilojoules. Think of your heat as part of your balanced reaction, right? It's related to everything else that's in there, okay? If I double the amount of moles of aluminum, then I'm going to double the heat that gets released with it, okay? Yep.
Will we get problems where it's like a mix between this and also need to calculate the change in rate?
Maybe. I'd have to give you different information though, right? But then as soon as I start to do that, we quickly turn a problem into like a 30-minute exercise, right? So we got to be careful when we see stuff like that. But in theory, yes, right? now that we 100% that problem, understand that problem, let's think about this one here. Give you guys a little bit of a hand here.
This is a combustion equation, right?
Mm-hmm. Burning some propane. While you guys are scribbling, just again, there's a nice keyword in there of excess, right? We already know which one's the limiting, so we already know what's gonna define how much energy gets produced. The limiting reagent produces the least amount of product, so in this case, we could also say it produces the least amount of the energy, right? Because energy is a product. So don't forget your limiting reagent type problems, okay? Yep. Mm-hmm. No. All it's saying is what it's telling us what to compare it to. It says heat. So we can convert grams into heat. So do we care about those? No. No, right? Because this is a product, this is a product, and that's a product. Right? So we need to convert, basically we're converting that into that. You could convert it into this, but that wouldn't tell us anything about the energy, right? That's part of it, yeah. Yep. Moles of this into there, right?
Now,
What did we do on the previous one?
I don't like.
Mm-hmm. No, 2 moles of this makes that much. Okay. Okay. You're kind of doing the same thing here because this isn't a 1-to-1 ratio, so that was just lucky, right? That was just fortunate. So good, we lucked our way into success, which is always good too, right? But here we need to convert that into that. So once you have the moles, just do the relationship for every 1 mole of this, then you have negative 222, or excuse me, negative 2,000.
So also 1 mole of C.
Mhm. Yep. 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 Yeah, looks good. Oh, whoops, I'm at done, but it's okay. It doesn't change your math. I misread my, sorry guys, this is actually 44, not 94. So, it's not gonna change your, I'm sorry about that. I just have bad handwriting. Sorry. I give myself 9 out of 10 points for credit. That's all. Yep.
Oh.
Yep. Yep, that's it though. Yep. I made this.
No, I corrected it.
Okay, then that did seem correct. Okay. So, so the C3H2. Yeah. No, it's okay. Cool, so let's just get this wrapped then. So using the correct numbers. So 500 grams of propane, C3H8. Convert grams into moles, 44.097 grams for every 1 mole. C3H8. And then for every 1 mole of propane, I make that much energy. Okay, or release that much energy. You guys with me on this? This is important. How do we know that these are the values to plug in here? That's from our balanced chemical equation, right? For every 1 mole of this, right, for every 1 mole of that, we release that much energy, okay? And my final answer was negative 2.52 times 10 to the 4th kilojoules. So about 25,000, right? All right. We will finish this up then. We'll finish up chapter 5 probably on Wednesday. Probably means Friday is a good day for a quiz on this stuff, right?